Okay, so let's take a look at that second page of that review. We've got another one of those interesting little piecewise defined functions on it with a little question of a graph that sometimes confuses people, but here we go. We've got a function here, and we're going to find all the numbers where the graph is not continuous. So again, just harping on that idea of what continuity means. So I want to find something where it's going to break the idea that the limit as you go from the left is the same as the limit as you go from the right equals that bridge in the middle. Well, the thing is this is a rational equation, and all rational equations are actually continuous on their domain. But the hint there is it's continuous on its domain. So the hint is let's find out where the domain doesn't exist. So let's see what we got. If we do a quick factor of f, we've got 5 on top. Can't do much on that one. So one thing it says is what type of discontinuity. We know it's not going to be a removable discontinuity because this is not going to be possible for that to cancel anything out. So I got my x minus 7 and I got my x plus 3, which is pretty obvious. And so what I know is that I've got two different versions, which is x equals 7 and x equals negative 3. Are my two discontinuities, and we should know that since they do not cancel out at all, those are going to be vertical asymptotes. That makes both of these things infinite discontinuities. Okay, sorry about the penmanship there. Okay, now moving on, kind of a quickie. The limit is you go to 2. Now keep in mind, as we've said over and over and over, the first thing you do for a limit is you just plug it in and see what happens. In this particular case, if we plug in negative 2, we got negative 15. If we plug in negative 2, we got negative 6 plus 2, which is, I guess, negative 4. So 15 quarters, boom. Nothing going down there. Now, this next one, we do have a little bit of an issue happening because we're getting close to negative 5. And if you did plug in negative 5 into the top, you're going to end up getting 0 over 0, which is one of those things you want to look at. Do I need to do work, or do I just say 0 over not 0, or not 0 over 0, or something else? Just please take the time to plug it into the numerator and the denominator before you just go crazy and start doing stuff. But this particular problem factors very nicely to 2x minus 3 times x plus 5. So keeping in mind that we're looking at those two things to kind of, quote, cancel out. Now they don't, we should know that that's going to be a removable discontinuity. So that means the limit as x goes to negative 5 on this, as long as I don't literally plug in the number negative 5, it's going to get infinitely close to negative 13. 2 times negative 5 is negative 10 minus 3. Boom, done. Now again, would it exactly be this coordinate? No, that's actually the whole. So this is going to be a removable discontinuity. It didn't actually ask for that, but it didn't ask for continuity anyway. It just says what was the limit. Now over here, just like the previous video, we know that we are looking for a very specific story. This says the sine of 4 theta. But I need to ensure that both the numerator and the denominator have exactly the same arguments. So since this piece right here says 4 theta, I need this piece right here to also be 4 theta. So I'm going to throw a 4 here and 1 in front. Again, properties of limits say if you put something inside, you can also then pull it to the outside. So technically the 4 was here, and I pulled it out. But we know that this limit right here is 1, so it looks like the product of those things is going to be then 4/7. Okay, last one for this video. Crazy story, all of this stuff happening. Man, there's so much going on here. This looks a little bit overwhelming. So I'm just going to kind of go through some things that I absolutely know for certain. This says that f of 3 is 4. So that means I actually literally have a coordinate. So f of 3 is 4. 1, 2, 3. See, 1, 2, 3, 4. 1, 2, 3, 4. F of 3 is 4. Okay, I got something. So I'm going to go ahead and take a look at that one. Let's see, I got that out of the way. This also says that as I get close to the number 1, from the right side, I'm going to infinity. Well, that right away tells me I'm looking at some kind of a vertical asymptote. I put that on the wrong side for a second. The limit as I go to the number 1 from specifically the right side is going to infinity, but the left side is going to negative infinity. So let's see, I'm going to go ahead and color that one pink so we can see that those two things go together. Okay. Now, I'd be tempted to kind of pull those things together, but I'm going to take my time here. Now, there's a couple other little interesting things. This says as I get close to -2, it's also going to infinity on both sides. So let's see. As I get close to -2, let me go ahead and label those asymptotes. Now, this one says as I go to, the limit as I go to -2 from the left side is infinity. -2 from the left side is going to infinity. And the limit as I go to -2 from the right side is also going to infinity. Okay, well, that's a little bit different than the previous one. They're both going up on both sides. Now, I'm kind of jumping around a little bit, but there's sort of a reason for that. This one says as I go to infinity, it gets close to -1. Well, that's actually the definition of a horizontal asymptote. So I've got this horizontal asymptote. Now, keep in mind, horizontal asymptotes can and sometimes will be crossed, but I don't know about this particular problem. So I just know that as I come this way, it's going to get close to here or here, and I'm not exactly sure if it's going to be on top or bottom, so let's just see what happens. And so I got this asymptote in. As I go to negative infinity, oops, it goes to +2. I just put that in the wrong place. Let's put it up here. As I go to negative infinity, it's going to +2. Let's fix that. And it says I go to positive infinity, it's going to -1 out here. So it's down here. Okay. Well, let's see what we got. So to connect the dots, and let's see, I have one more thing. As I get close to 3 from the right side, it gets close to 4. Oh, that's interesting. So it's definitely coming in here like this. So as I get close to 3 from the right side, it's getting close to 4. And as I get close to 3 from the left side, 1, 2, 3, it gets close to the number 2 right in here somewhere, but it's not going to touch it. Now notice that one was a solid dot before because we had that solid dot. And so now I think we can kind of finish it up. I'm going to go ahead and connect those two dots. This one can come in any way that I want, but I think a simple S curve will do. Over here, I want to combine this one with that top line right here. But if somebody wanted to come in underneath and come back up, that would be sufficient. And then I think over here, I'm going to do the same kind of idea and just have it kind of come down here and connect up like that. So, you know, I had a little bit of guessing around as to what I think that should look like, but I think I've come up with a solution that fits. As I go to infinity, over here, it's getting close to -1. That looks pretty good over here. Should maybe bring it down a little bit. As I go to negative infinity, it's going close to +2. As I approach 1 from the left, right here, it's going down. 1 from the right is going up. F of 3 itself is 4, a nice solid dot. As I get close to -2 from the left side and the right side is going up. As I approach 3 from the left, it's getting close to 2. Notice the jump. And as I approach 3 from the other side, it's 4. So they're showing a little continuity over here, but not over here because of the jump. And I think we're done with page 2. All right. I'll see you back for the next one.